Okay, y'all get it? It's not a quiz or anything.
Oh, okay.
Yeah. Okay, so first derivative. What we're going to do is we're going to try and figure out where this function is increasing and decreasing, where it's concave up and concave down. All right, so first derivative, 5/3 x to the 2/3 minus 10/3 x to the negative 1/3. Right, that's just power rule. Oh, that's f prime. F double prime, we just do it again. So what do we get here? 10 ninths x to the negative 1/3 plus 10 ninths x to the negative 4/3. So those are your first and second derivatives respectively. Any questions on that part? Okay, so now we're trying to find where it's increasing and decreasing. So let's take our first derivative, set it equal to 0, and we also have to figure out where the first derivative does not exist, right? Those are the two things that we're going to look at. So let's set it equal to 0 first. 5/3 x to the 2/3 minus 10/3 x to the negative 1/3. So any ideas on an approach for this to try and set this equal to 0? Factor? What do they both have in common? Like if that was like x squared and x cubed, you could like pull out an x squared or something, right? Well, how about this? Just tell me if you agree with this or not. 5x to the 2/3 over 3 minus 10 over 3x to the 1/3. That's just me using properties of exponents, right? The negative exponent means drop it down. And now let's get a common denominator so we can put these two fractions together. So what do I have to introduce on the second or on the first fraction here? X to the 1/3. So I'm going to multiply by x to the 1/3 here and x to the 1/3 here. Is that good? So I'm doing this problem because I want you to see, like, this is just algebra, right? The calculus is done. Like, the calculus part of the problem is done. This is the algebra that's required to continue, right? So show it to you one time, now you know kind of, oh, maybe I have to do this. All right, so I'm going to put these together. What happens when I multiply the numerators out here? What do you do with those x's? What do you do with their exponents? You add them, right? It's 1/3 plus 2/3. 1, right? So that's just 5x. Okay. So I have 5x and minus 10 over the common denominator, which is 3x to the 1/3. With me? And that's equal to 0. So all I have to do is set the numerator equal to 0. We talked about that already. And solve that, you get x is 2. So I have a critical number, right? 2. Now, in all the other problems that I've done, I think up to this point, we have never had this come into play, have we? This is not come into play? It's about to come into play, all right? Because we need to ask ourselves where the derivative doesn't exist, right? So let's say this right here, this all goes with this, right? But now this part, okay, I'm going to do that right here. I want to know where the derivative doesn't exist. Well, this is the derivative, right? But and if I look at that, I may not be able to see that there is a problem. So what if I simplified the derivative out to this again? Okay, so I'm not setting it equals 0. I'm just looking at it. Yeah. So where's the problem? If x is what? 0, right? If x is 0, I get division by 0. That's no good. Now, I'm going to put x as 0, but we need to ask ourselves, was 0 in the original domain of the function? Because if 0 wasn't even in the domain to begin with, then we don't have to consider this. But you can plug 0 into this, right? 0 here, 0 here, you get 0. So 0 is actually part of the domain of the original function. You can plug it in and get an answer. But you cannot plug 0 into the derivative. It's undefined, which means we have a corner or a cusp there. We have something happening to the function. All right, so this is a second critical number. With me? Okay, questions? No? I know it's Monday, but we're here, right? Okay, so I now need to do what? Once I've found the two critical numbers in this case, what am I going to do with them? Number line, right? Do a number line. And I'm going to do some test points and plug those test points somewhere. All right, so let's see. Number line, it was 0 and 2. Which creates a nice natural partition of my number line into 3 regions. I picked some test points, like let's say -1, and 1's a good one, and let's go with 3. And now plug them in. I'm plugging these into the first derivative, right? I'm plugging them into the first derivative. See, students start to get a little confused because, you know, the method that we had for finding the maximums and minimums of a continuous function on a closed interval is that you found the critical numbers and then you plug those into the original function and you plug those into, and then the endpoints into the original function. Students start to like forget, does this go into the original function? Does it go into the derivative? Just try and remember what we're doing. We're trying to figure out if the function goes up or down, right? So I need to know where the derivative is positive or negative. All right, so we're plugging these in, and I get to plug them into the derivative. I'm going to rewrite the derivative over here. This seemed to be the version of the derivative that was the best to work with, right? This one. It was x to the 1/3, right? It was same thing as cube root of x, isn't it? That's what x to the 1/3 means. Okay, so let's plug -1 in here. -1 here, get -5, -10, I get a negative on top. And then carefully, what's the cube root of -1? What number times itself 3 times gives you -1? -1, right? Cube root of -1 is -1. Square root of -1 is undefined, right? That's an imaginary number, but cube root's okay. So we get a -1 on the bottom, so negative over negative, that's positive. This means my original function f is increasing here. All right? Now we plug 1 in. So 1 goes in here, get negative on top, 1 here. Cube root of 1 is just 1, so we get a negative. It's switching. That doesn't mean I can switch though, right? I can't just say increasing, but I'm pretty sure it will this time. Let's see, 3 in here, I get 15 minus 10, I get a positive on top. And then the cube root of 3 is a positive number. That's all I care about, right? Cube root of 3 is a positive number. I don't necessarily need to know its value. So that. So my function goes up, then down, then up. Let's go ahead and answer the questions while we're here. Where is this function increasing?
Over -1.
Okay, so anything over here though, right? Mm-hmm. Anything over here. So to the left of 0 and to the right of 2. Agreed? So to the left of 0, negative infinity to 0, union to the right of 2, 2 to infinity, like that. Where is it decreasing? 0 to 2. Okay. Now, do we have any local maximums? We have a local max. It's at 0. So the way I like for you to do that is to write f of 0 and then plug 0 into the function, original function, to figure out what the y coordinate is. And it's 0, isn't it? And then we have a local minimum, because it goes down then up, right? Local minimum at f of 2, which would be, f of 2 is the, isn't that the cube root of 2 to the 5th minus 5 times the cube root of 2 cubed? Okay, so I'm plugging 2 into the original function. And remember that cube root, right? I'm sorry, a fraction, the numerator is the power and the denominator is the root. So do y'all follow that?
But wouldn't it be 2 squared?
Why is it 2? Oh, did I put? Oh, squared. Yeah, thank you. Squared here. And, well, that's the exact answer, all right? I mean, if I go and I try and do anything else, I'm going to get a decimal. I mean, I could clean up these radicals a little bit because cube root of something to the 5th power, you can take out groups of 3. So I could pull out one group of 3, which would be a 2 out here, cube root. I would still have how many 2's in here? 2 of them, right? So 2 squared, that's 4. So minus 5 times the cube root of 2 squared. All right, that's about, I could turn these into 4's, but that's about the best I could do as far as an exact answer. Right? Well, I could probably clean that up a little more also. Yeah, I could subtract those. Let's do that. This is 2 cube root of 4 minus 5 cube root of 4. Isn't that the same thing? And those are like radicals. So I could say it's negative 3 cube roots of 4. Or get my calculator out and get the decimal. Understand? Sure? This is the minimum value, whatever it is. Okay, we are done with that part. Figured out where it's increasing, decreasing, local max, local min. One thing to be careful with here is remember that 2, was it 2? No, it was 0 where we had the derivative being undefined, right? If 0 was not in the original domain of the function, right, we would not have considered that. Agreed? We would not have considered that. But you never want to try and, what was the point I'm trying to make here? No, let's wait till we see one like it. I don't want to confuse you until you see it. Never mind. All right, let's look at the second derivative. Second derivative, set it equal to 0. So now that I've kind of shown you on that first derivative how to attack it, I could rewrite this second one as 10 over 9 x to the 1/3 plus 10 over 9 x to the 4/3. Set that equal to 0. So what I'm doing right now is I'm setting the second derivative equal to 0, and I am trying to figure out where the second derivative doesn't exist. Right? That's what I'm trying to do right now. So first I'm setting it to 0. I rewrite it. And let's do common denominator again. So we multiply the first fraction by what?
X to the 3.
X to the 3 over 3, which is just x, right?
Yeah. That's what I
See, if I multiply this by x to the 3 over 3, I get x to the 4 over 3, because I'm going to add the exponents. Right? That's what would happen if I put those together, 4/3. But 3 over 3 is 1. Right? So I'm really just multiplying the top and bottom by x. That's all I'm doing here. So this I had to introduce myself. So what does the top now become? 10x plus 10 over 9x to the 4/3 equals 0. All you have to do is consider the numerator. So 10x plus 10 equals 0. And so x should be negative 1. So we have a critical number here with the second derivative. And that was this part, right? That was this. Now I need to figure out where the second derivative does not exist. Can you tell by just looking? It's right here. This again, 0 again, right? So x is 0. We got some interesting stuff happening at 0. So when we graph this, which we'll graph it real quick. It should be pretty interesting looking. Okay, number line. Make sure you put these in order. -1, 0. Test points, we'll go with -2. We'll go with, no way to avoid it. We've got to go with the fraction there. -½ and let's say 1. And these go where? Second derivative. Second derivative at -2. Second derivative at -1/2. And second derivative at 1. I'm going a little faster through this second derivative. I'm going to plug it into this, all right? That's my second derivative cleaned up. Ignoring the 0 for now, just that's my second derivative. Now, I want you to pay attention to something in the denominator here. This x to the 4/3 really means the cube root of x to the 4th power, right? When you do x to the 4th power, it's going to be positive. And when you take the cube root, it's still going to be positive. So would you agree that 9 times a positive number is always positive? So the denominator we really don't need to worry about. It's always going to be positive. So in all of these, it's positive on the bottom, right? Positive on the bottom, positive on the bottom. We just need to figure out what's happening on top. That make sense? Okay, so -2. If we plug -2 in here, it's negative on top. Plug in -1/2. That'll be -5 and then +10, so we get a negative on top? No, positive. Well, I can fix that. Positive, and then if we plug in 1, we get positive again, right? If we plug in 1, get positive. So this thing does this. It's negative, then it's positive, then it's positive. So it doesn't switch there. So remember, the sign of the second derivative tells us about concavity. So this tells me that over here we're concave down, f is concave down. Here we're up, and then we're going to be up again. I already have an idea of what's going to happen at 0. Remember, 0 is where the first derivative didn't exist? Check back on the stuff we had. Did the function at 0 go up then down or down then up? Probably went up then down, right? So just imagine this. Our function has to go up and down at 0, and it has to be concave up the whole time, which means it's got to look like that. See that? Smile, smile, up then down. That's the only way it can happen. But I mean, I'm getting ahead of myself here, okay? All right, so where's the second derivative? I'm sorry, where's the original function concave up? Where is it concave up? Yep, you can just say -1 to infinity. From -1 to infinity, it's concave up. Where is it concave down? Negative infinity to -1. And then we don't talk about local max, local mins with second derivatives. What do we talk about? Inflection points. And there's not a distinction between, like, you know, local max and local min were like local max was up then down and local min was down then up. With inflections, we don't care if it was down, up, or up, down. Just if there was ever a change down to up, we have an inflection point. So we have an inflection point. I'll just put IP for inflection point, and we just put the x value. You don't have to actually plug it into the function. If you'd like to, you can, but you don't have to. So x is -1 would be our inflection point. Okay, that's it. What do y'all think?
That's one full problem.
What's that?
That's one full problem.
That was a wonderful problem?
No, that's one full
Oh, yeah, that's one full problem right there. Yeah. I thought you said wonderful. But I think both. I think it was both a full and a wonderful.
One full problem.
All right, I like that one. Graph it. Let's graph it. I don't know, the internet's been really slow here today. All right, so it was, now I will say this, before we graph this, that computers do have problems with these rational exponents, all right? I have seen computers only graph part of these functions before because it has trouble with certain things. So just as a little asterisk here, I'm not sure if this thing is going to give us the whole function or not. We'll see. I think it'll do okay because they were cube roots. It really has problems more when it's square roots or like even roots, like fourth roots. So if that would have been like the original function would have been like x to the 3/4 instead of like 4/3 the other way around, usually the computer doesn't deal well with the negative parts. But I think it'll do okay here. So x raised to the 5/3. Whoa. Okay, this thing's too smart. Minus 5x to the 2/3. I'll try that. Yeah. What's that? Where did we have, so does this match up with what we had? Was it increasing from negative infinity to 0? Was it decreasing from 0 to 2? And increasing from 2 on, right? Okay. Now, concavity, it's very hard to tell from here, but we were concave up where?
-1 to infinity.
-1 to infinity. So -1 is right here, right? This is -1. So right around here, you said it was concave up there?
Yeah.
Or concave down? It's concave up from -1 to, or negative infinity to negative.
-1 to
Okay, -1 to 0 is concave up. So this little part right here looks like a smile. Okay?
Negative infinity to -1.
Negative infinity, -1 is concave down. So it's hard to tell from this picture, but it actually does this. I mean, it's coming, well, I'll exaggerate it, okay? It's coming in like this. Does that make sense? Now, I've exaggerated it, but this looks almost like a straight line, doesn't it? But it's not. It's got curvature to it. And we know that because that's what our information told us, right? Yes? That just makes me think real quick. What if you had a straight line? Then what's the concavity of a straight line? Okay, so look, let's just real quick look at a function. 2x plus 1, right? That's a line.
Yeah.
Take the first derivative, second derivative,
No.
which means that your concavity is not positive or negative, it's 0. When your concavity is 0, you have a straight line. Okay, so we need some sort of positive or negative concavity to have curvature to our function. All right, what else? We have our cusp. We got our cusp, and then, yeah, it all looks good. All right. I wonder if I zoomed out if I could see that concavity better. Nah, not really. Well, it kind of looks curvy. I think I could do it maybe if I did change my x to like -5 and my y to 5. Still not doing it. I might get it with that. Where was it at -1?
Yeah, because it goes up.
Yeah, so you can kind of see there's like this happening here, and then like that. There's no way you can get that from a graphing calculator. You know what I'm saying? Like, you can't, yeah. So that's where, you know, we talk about, well, why do we need to do any of this if you have a computer? Because there are limitations, you know? I mean, we know where we have an inflection point. If I just asked you to graph this, I'm not sure you could tell me where the inflection point was. You might miss that, right? Okay. All right, let's look at, let's do one more example.
That was the graphing of the second derivative, right? You just graphed on Desmos?
No, I graphed the original function.
The original function.
That was the original function. Yep. Which is our goal. Our goal is to graph, but on this test that's on Wednesday, I am not going to ask you to graph. All right? That will be on the final, or it will be part of a take-home. The graphing, as you'll see, is a very long, tedious process. Kind of like those problems I sent you home with already that are due on Wednesday. Okay? Those take a little while, so you won't see the graphing on this test, won't see it on the final. It'll be a take-home portion. But what I've decided is we're going to have this on the test, all right? This will be on the test. And then there's one other thing I'm going to put on the test that we're going to talk about today that I think you'll be okay with. We'll see. All right? All right, so do y'all want to graph one more? Okay, let's do, I just want to pick something that's kind of crazy looking. All right, I'm going to pick number 44, which is the ugliest looking problem. It's the last problem of the problems that they give, so let's see how bad it is. F of x equals, oh, wait a minute, hold on. Oh, yeah, this will work. Arctangent of x minus 1 over x plus 1. All right, there's a lot going on here. All right, there's a lot going on. I have not done this problem, so I'm not sure what we're gonna run into here. All right, we need the derivatives. So first, we need to remember what the derivative of arctangent of x is. Arctangent of x. Yeah, I covered this very briefly when I showed you the derivatives of the inverse trig functions, and I told you to put a star next to this one because this one comes up a lot. 1 over 1 plus x squared is the derivative of arctangent of x. So if we wanted the derivative of arctangent of this, it would be 1 over 1 plus all of this squared, agreed? Times, chain rule now, right? The derivative of what was in here, which is a quotient rule. So times, now I'm going to do the quotient rule right here. I already know the bottom is x plus 1 squared, right? So I do derivative of the top, which is 1 times the bottom, minus the derivative of the bottom, which is 1 times the top. Good? Sure? All right, cleanup time. 1 over, we have to set this to 0. That's why I want to clean this up. I'm going to write this as x minus 1 squared over x plus 1 squared. I'm just rewriting this. I'm squaring the top and bottom separately. Excuse me. What does my fraction over here become? 2 over x plus 1 squared. Yeah, because this distributes, right? So you get minus x plus 1. So the x's cancel, x minus x, and then 1 plus 1.
Nice.
We good? All right, this looks pretty bad, doesn't it? But check this out. This right here is multiplying times this, right? So multiplying two fractions, you go straight across. So how about on the top, I just get 2. And on the bottom, when I multiply this times the bottom here, there are 2 terms down here, aren't there? 1 plus this. So this will go to the 1 first and become x plus 1 squared. And then what happens when I multiply this times this one? They cancel, right? The x plus 1 squared, you can look at this as being like over 1 if you want. When you go like here to here, the x plus 1 squareds cancel. And all you're left with is the plus and then the x minus 1 squared. How's that? All right, how about this now? 2 over x squared plus 2x plus 1 plus x squared minus 2x plus 1. So what did I do there? Just expanded those out, right? I just squared x plus 1 and got this, and I squared x minus 1 and got this. And I did that because I knew that because this was a plus and a minus, some things should cancel. And you can see it right there, right there. So we get 2 over 2x squared plus 2. They all have 2's. So I can reduce everything by 2. Huh. Very interesting. That's the derivative. Kind of weird, actually.
That's like the.
That's the derivative of tangent of x, isn't it?
Yeah.
Or our tangent of x. Okay. It's just because the way the problem was written. All right, there it is. Good? Questions? All right, let's take the second derivative now. The second derivative won't be as bad, right? Because all we have to do is take derivative of that. So the second derivative, how would you all like to do that? You want to do quotient? Or do you want to bring this whole thing up like a negative power and then chain? It doesn't matter. Quotient? Want to do quotient? All right. So what's derivative of the top? 0 times the bottom, it's 0, right? Minus the derivative of the bottom, which is 2x, times the top, which is 1. So just negative 2x on the top. So I'm doing that in my head now because we are like almost done with calculus 1.
Yeah.
Like we've been doing chain rule. You've done all that homework, right? You've become pretty proficient with quotient rule now. So derivative of the top, 0 times the bottom, who cares? Minus derivative of the bottom, 2x times the top, 1 gives you negative 2x over the bottom squared. Now you might, I'm saying I'm doing it mentally here kind of, but you might need a little time. That's fine, but you need to know what to do. You can't look at that and be like, well, I don't know how to take derivative of that. All right, that's it. We've got our first and second derivatives. So let's mess with these. Let me take this one over here, 1 over x squared plus 1. And then, so there's our derivatives. The first step is to set the first derivative equal to 0. So let's set the first derivative equal to 0. And that means I'm going to set 1 over x squared plus 1 equal to 0. And not going to happen. Right? I can't get 0. I can't make that 0. Right? Because I'd have to make the numerator 0. The numerator is 1. 1 can't be 0, so that's not going to happen. So there's no solution. How about the derivative not existing? Okay, so is it possible to look at this derivative? Is it possible for you to plug in an x that's going to cause a problem there? No, you can't, right? You can't do anything here. So there's nothing, right? Nope. Which means we don't have a critical number. That's a problem because we were using our critical number to see where it's going up and down, right? But we don't have anything. So what do? I need a number line, right? I'm supposed to put my critical numbers here and then pick test points. I don't have any critical numbers. So that means I get to just pick any test point I want. And whatever the answer is here is what the function is always doing. Okay? So let's plug 0 in. Now, we never talked about the domain of this function. We never did. But maybe I can help you. If you remember back in pre-cal, the graph of tangent was like this. This was tangent of x. And if we looked at tangent of x, actually it kept going both directions, right? But when we defined arctangent, we had to restrict the domain between negative pi over 2 and pi over 2 here. So the the domain and range of tangent reverses switches. I feel like I've shown you all this. Did I? Right? Tangent goes this way. Arctangent goes the other way. So we restrict the domain here between negative pi over 2 and pi over 2. And then over here it spits out everything, negative infinity to infinity. So the range of tangent, the outputs are from negative infinity to infinity, right? That means that the domain of arctangent is anything. So when I was over here looking at this, and I was like, well, wait a minute, are there some restrictions here that I can't plug in? The fact that it's arctangent means any number here works, any number. But there is one number that's not in our domain. There is one number that's not in our domain. What is it? -1. -1 is the only number that is not in the domain of this function. Do you agree? Yes? Okay. I need to keep that in mind. But I'm moving ahead right now with the derivative, all right? So I'm going to try and plug 0 in. I could have picked any test point. Now, had I picked -1, I would have run into a problem. Well, because it's not in the domain of the original function. Would it have caused a problem with our derivative? -1? I would have squared it, it would have become 1, and this would have been 1/2, right? That would have been potentially a bad situation. So that's why when we get to the graphing, we need to look at this like holistic picture, starting with the domain of this, and then we talk about a lot of things that we did in like pre-cal and algebra, and then we get to the calculus part. But let's plug 0 in. What happens if you plug 0 into the derivative? So what's f prime of 0? F prime of 0 is 1, which is positive, right? This means that my function is increasing, right? It appears everywhere, doesn't it? It's always increasing. However, we do need to keep in mind that -1 here. We cannot say it's increasing everywhere because that -1 is not defined, right? So you can't say it's increasing everywhere if there's a point in there that you can't plug in. So I'm gonna when I get to the point where I write out where it's increasing, decreasing, I'll do that. Let's talk about the second derivative. All right, let's do that, and then we'll put it all together. So second derivative equal to 0. So that just means that -2x has to be 0, which means x is 0. So I do have a critical number here, right? And do we have a place where the second derivative doesn't exist? No, right? Second derivative is always defined because it's impossible to get division by 0 here. So I only have one critical number. It's at 0. So I pick, ooh, yeah, see? This would have been problematic because your instinct would have been to plug in -1, right? Maybe? Or unless you want to do like -pi or something. But I can't plug in -1. I'm going to plug in -2 then. All right? And I'm going to plug in, here I'll plug in 1. So let's make a note of that. Let's put up here, let's just add to this. Domain of f, right? X cannot be 0, right? So it's all x, not 0. X cannot be -1, right? Just keep that in mind. X can't be -1. All right. Our function is undefined there. Undefined. We have a hole there, right? I wonder if we have an asymptote. I wonder if we have an asymptote. Well, who cares? We'll come back to it in a second. -2. We actually don't, but -2, we plug -2 into the second derivative, and what would happen? -2 times -2 is +4, and this squared is always positive, right? So it's going to be positive. So concave up. So f prime of -2 is positive over positive, which means that our original function is concave up. And then if we plug in 1, I'm assuming that it's going to be negative. So negative on top, positive on the bottom, so it's concave down. We have an inflection point, don't we? at 0. All right, let's try and summarize this now. Where is f increasing? So where is it increasing? Everywhere except negative 1, right? That's tricky, you see? Because if you put negative infinity to infinity, I mean, technically it's not correct. Where is it decreasing? Nowhere. Ooh, how do we say that? How do we say nowhere, other than writing the word nowhere? So I'm asking, when we say where is it increasing, we're saying, give me the set of points where we have a slope of a tangent line that would be positive, right? Give me the set of points where the slope of the tangent line is positive. This is saying, give me the set of points where the slope of the tangent line is negative. And there is nothing. There are no points in that set. So it is the set that has nothing in it, which is called the empty set. You know the notation for the empty set? 0 line through it. That's not the military version of 0. Because I know in the military they slash the 0 like that. It is, but in this context, it is the empty set. If you put here 0, it's wrong, like the number 0. That's the empty set. I mean, everybody knows, like, has seen this notation, right? Double struck, capital R. That's like the shorthand notation for all real numbers. Well, if you're going to use that sort of notation, then you need to know this notation, which is basically the complete opposite of all real numbers. It's nothing, right? So we look at sets as like bags, and so you're saying what's in the bag, right? If you say this, it's every real number is in the bag. But if you're standing there with an empty bag, this is the notation for it. That does not mean the number 0. If I take the number 0 and I put it in the bag, I have the number 0 in the bag, right? That's not this. Yeah? Okay, all right. You got it? I think I overkilled it there a little bit. Okay. But 0 is a number, right? So my bag has a number in it. It's the number 0, right?
Yeah.
Yeah, okay. All right.
The empty set doesn't even have 0.
That's right. The empty set is an empty bag, right?
Yeah.
So, and the bag doesn't even have to hold numbers. Your bag could hold functions, right? So you could have, if you have this later on, you talk about, okay, show me what is the bag that has all continuous functions in it, right? So all continuous functions are in this bag. That's actually, there's notation for it. But you could say, what about all the differentiable? Put all the functions that are differentiable, but not continuous. That's impossible, because to be differentiable implies you're continuous. So if I say, show me the bag that has all the differentiable functions that are not continuous, that is going to be an empty bag. So it's going to be the empty set. All right, we're going beyond. All right, we've answered the questions, right? Do we want to look at the graph? I'm curious to know what's happening at -1. I'm really curious to know, right? I'm so curious that I'm actually going to consider this real quick. What would happen if I go to -1? What would happen if I take this limit? What happens as I go to -1? So tell me what happens to the numerator in here. Where does that go? -2? Where's the bottom headed? 0. Uh-oh. We have fixed over 0, right? A fixed number over 0 inside of an arctangent function. Fixed over 0. What are you tell me. If you get fixed over 0 in a limit, what's the
Negative.
It can be either positive or negative infinity. That's what it can be. Positive or negative infinity, or it cannot exist. So let me go and let me try something. Let me come in from one side. Let me come in from the left side. How about that? Yes? So now what I'm doing is I'm taking the number line, I'm coming in to -1, I'm coming in from the left. So I pick a number in here like negative 1.001. Be careful, know where you are here, right? 0's here, so -1.001 is over here on the left side. If I take that number, does this look familiar? I mean, we've done this in the past, so I'm assuming this looks familiar to you. Okay, so if I take this number and I plug it in here, what's my numerator going to be? Is it going to be positive or negative? Negative 1, still be negative on top, right? So I'm still going to get negative 2 on the top. If I plug in this here, am I going to get a positive or a negative when I put those together? I'm going to get a very small negative number, right? So you're going to have a number that's getting close to 0, but it's negative. So you have a negative over negative, which is positive. So I know that if I come in from the left, right, that this thing is going to what? It's going to positive infinity. Now, what would happen if I do that same limit, arctangent of positive infinity? Forgot that part. That's critical. Because what's arctangent of positive infinity? What? You can't plug infinity into arctangent. Can you? Arctangent spits out an angle, doesn't it? Arctangent spits out an angle? So when I say like arctangent of 1, aren't you saying at what angle is your y coordinate divided by your x coordinate 1? Isn't that what this is saying? So if I go to my unit circle right here, my x and y coordinates are both root 2 over 2, root 2 over 2, right? So the ratio of those is 1. So arctangent of 1 is pi over 4, right? This is saying arctangent of infinity. What? Go to your tangent function. These are the angles, right? These are the outputs. It's saying when is your output infinite? At what angle? Pi over 2. Pi over 2. This is a limit. As x approaches negative 1 from the left, this thing goes to arctangent of infinity. Arctangent of infinity is approaching pi over 2. It's approaching it. It's not ever there. So this limit is pi over 2. And then we could approach 1 from the right and do the same thing. I'm just trying to show you we're not going to have an asymptote there. When I graph this at negative 1, we should be getting close to pi over 2. So you remember when I said we're not going to have an asymptote there? That's what I was thinking when I looked at that. I was, okay, the limit is going to give us that pi over 2. So that's where I'm coming up with it. It's not obvious. Okay, so now arctangent of x minus 1 over x plus 1. Interesting. Okay. Well, as we came in from the left, it was approaching what? Pi over 2 at negative 1. And when we came in from the right, we never did that limit, right? But that was going to approach negative pi over 2. So you have a function that actually has a jump in it. I don't think we've ever looked at a function that has a jump like that that's not a piecewise function. This is just a regular old function, and all of a sudden it has a break in it. Keeps going. Pretty cool. All right, where was it increasing?
Negative 1 to negative infinity.
So I think it was negative infinity to negative 1, right? So look, it is going up here,
Yes.
and then we have to say at negative 1, it's still going to increase after this, but there's something that happens. So we come down here, now it's increasing, and it still increases, right? And then we had a change in concavity, and that happened at 0, didn't it?
Yeah.
It's right there. Smile, frown. See it? Okay. That wasn't as bad as I thought it was going to be.
How do you notate the jump? Like, do you have to notate that jumps in there when you write the sequence down for the infinity to negative 1?
Well, that we did. When we were saying where it was going up and down, right? We said it's increasing from negative infinity to negative 1, union 1 to infinity. That's how we designated that. You could argue with me, or with anyone, that this function is always increasing, right? So you say to me, oh, this function's always increasing. And I would be like, okay, what about at negative 1? Then you say, well, wait a minute, negative 1's not in the domain, so never mind. You know? So that's why you have to have that negative infinity to negative 1 union negative 1 to infinity. You have to somehow account for that domain issue. All right, I think that's it. Do y'all feel like you can do your homework for that? 4.4? Section 4.4? Now I will, let's talk a little bit about the types of problems I would ask you from 4.4. I'm basically going to go back and look at your homework assignment for that. Does anyone have the homework assignment for 4.4? Because I have a bunch of stuff circled on my page. I don't know which is homework and which is just other stuff. Anyone have that with them? Will you read it off?
I have a problem.
Is it 5, 8,
5,
6?
11, 19.
11, 14,
Whoa. 5,
11.
14.
Oh, wait, 4, yeah. 5, 11, 14, 19, 22,
23,
Or 4,
Oh, 4.
4, 4.
Yeah, so.
That's what I have for sketching the curve. She has 5, 11,
Wait.
14.
Oh, wait. Oh, I'm sorry. I'm looking in 4.4, but I mean 4.3.
Yeah.
I apologize. So
It's confusing.
4, 5, 7, 8, 25, 27, 20. So if you look at the problems from 4.3, what I ask you on the test will be similar to what you see there. Some of the problems I've been doing here are from 4.4 because I'm trying to get you to start to get to the point where we're going to graph these. All right? We're not just not going to do the graphing yet. So look at your homework assignments for 4.3. I think they're a little easier. Like the first couple are all polynomials, so derivatives are very clean, but some of them do get a little more complicated. All right? All right, so what I'm going to do now is I'm going to do something that I think we can squeeze into this test that I think you'll enjoy. Yeah. What the heck is this? All right, that's not it. I want to do Newton's method. All right. So do you remember me telling you like how your calculator solves problems? Right? And if in certain calculators you have this solve function. So I'm gonna show you this method called Newton's method. And I think I need to reevaluate this notebook real quick. Start it all over. All right. So let's say we are trying to solve this problem of x squared minus 2 equals 0. I know we could just say, all right, well, x squared equals 2, and then we could do square root on left and right, do plus or minus, right? And then we would say x is equal to plus or minus root 2, and that would be the exact answer. I mean, right? Two solutions. But what is the decimal approximation to that? So that's when you go into your calculator and you take the square root, right? So when you type in square root of 2 on your calculator, what is your calculator doing? Like, what is it actually doing? Well, here's what it's doing. Here's a visual representation of what Newton's method is. Okay, that is the graph, okay? This is the graph right there of, we were trying to solve this equation, right? Like, look at the left side and call that f of x. That's the graph of it right there, okay? This is the parabola. F of x equals x squared minus 2. And what we're trying to find are the x-intercepts of this. The x-intercepts correspond to setting it equal to 0, right? So I'm trying to find this point. So the way Newton's method works is this. First thing it does is it picks a random point, right? So I'm going to pick a random point and plug it in. So actually I'm going to take f of 3. We plugged in 3 here, okay? We plugged that into the function, right? That was a guess. We guessed that the answer was 3. We plugged it in, and we got an answer, right? Here's the answer we got when we plugged in 3. What would it be? 9, 7, right? So we get 7. Newton's method then does this. It takes the tangent line at that point, okay? So it takes the tangent line. It extends that tangent line down to where it hits the x-axis. You see that right there? That is now my second guess. Okay? And now what I'm going to do is take that answer and plug that into the function again, and then take that tangent line and drop it down to see where it hits the x-axis. So what this is, Newton's method is an iteration. That's not what I was going for, but I will say it. It's an say it?
Iterative?
Iterative. There we go. I couldn't say it. Iterative process. All right? It's using the fact that the calculator can do computations very fast, right? So the calculator says, computers can go, okay, guess 3, function's value. It calculates the slope of the tangent line, and it actually gets you the point here. Now I'll show you how that computation is done. Then it says, okay, take that answer, go up, go back down, go up, go back down. And what it's looking for is the distance between these two results to be small. So right now, the distance between these two is really big, right? Mm-hmm. So we've gotten the next distance. So this was our first distance, and then this is the second distance, smaller. Now let me do it again. Third iteration. Okay, it's getting hard to see, so I'm going to zoom in. All right, so there was our second one. Here's our third one, I think. Maybe zoom in. Yeah. And now, man, it's right on that little dot. See, I worked it out. I wanted this to show up right on that little dot on the board. Okay, so you can see our next answer went in and over. Man, we are really close to that x-intercept, aren't we? So I'm going to zoom really, really far in. And it's still really close, isn't it? And I've only done, like 3 or 4 iterations. So if I do maybe 5, you can't even see them in there. But I want you to see here, let me back up to 1. When we did 1, zoom out, zoom out. Okay, so when we did 1, right, our guess was 3, right? And it's gonna spit out a second number. This was this, so 3 went in, came out, and we got this, right? That was 1.83. And then if I do it again, it goes up and over, and now I get 1.46. What's the square root of 2? It was like 1.414, something like that. Like if you type into your calculator, this is what your calculator is doing. It's getting the next one, man, that looks terrible. 1.41439 something. Let me go 6 in here. 1.4142135.6, right? And what it's looking for is there to be like no significant change within the first 8 decimals. So if I go another, see, look, did y'all notice nothing happened here? Let me go back. I know it's hard to see out there, but. Okay, this one goes out, it goes 3780. If I go one more process, 373, that 373 didn't change, right? Go again, that 373, a lot of this is holding, right? So what your computer is doing is it's saying, keep doing this until, and this depends on whoever wrote the code, the program, says there's the difference between, if you take this one and you subtract the previous one, that difference is, smaller than 0.0000, maybe 10 zeros, something, right? So however many significant digits you want, you get to adjust the precision. That's pretty neat, right? So do you remember me showing you the method where you go and you take the interval, then you cut it in half, and then you cut it in half and cut it in half? That works, but it takes a long time for it to actually narrow that down. Newton's method is much faster. In computer science, we call that big O. Big O, it's like your operation count. And your big O has different orders. It's like, I'm not a computer science person, but I know we did do this in the math. We had to program stuff. And we had to program Newton's method into a computer. Well, I did it here too. It's not hard. The algorithm is very simple. Okay. All right. You get the idea? Sure. All right. So let me just give you Newton's